All right, today we are going to be learning about nuclear equations, and we're looking specifically at alpha and beta decay. So we are going to be drawing out what these equations look like. So we're going to start off with what exactly are alpha and beta particles. So we'll start off with alpha. So alpha particles are essentially just going to be a helium nucleus, and that is represented by the following symbol. So that can either be written as this, or you can write it as this, with this being the alpha symbol here. Okay, we also have our beta particles. Okay, I guess I should have written that as singular. We'll make that singular there. Okay, beta particle, we have that can be represented by the following symbol. This being the symbol for beta. Or we can write it like this because it's really just a high energy electron that's emitted during radioactive decay. So these are emitted during decay. All right, so let's look at what these numbers mean here because we might not be familiar with that. So we have A versus Z. A and Z. So A is written as the atomic mass, and Z is written as the atomic number, which also represents the proton number. Okay, let me make that a bit clear. All right, so we have A and Z. So A is going to be written, let's start off with alpha decay. Okay, so for alpha decay, we have our parent isotope here, so our parent atom, and we have that written as A and Z. So we have our atomic mass and atomic number, or proton number, and X will represent the element symbol. That will decay or break down into atomic mass minus 4, and then Z minus 2. Oops, make that a 2. Okay. We'll have Y represent our daughter isotope. This is our daughter. So our parent isotope, our daughter isotope, and finally we have our alpha particle, and we know that's written like this. So it's just helium nucleus. Okay, so we have our alpha particle. Okay, so this is the general equation for alpha decay. So now that we have this, let's do a couple of examples here. Okay, so we have 218 polonium. Okay, so we have an isotope of polonium 218, and it is radioactive. So we need to figure out the atomic number before we can proceed with this. So we find polonium on the periodic table. So polonium is going to be, let's see if I can find it. There it is. There's polonium, atomic number 84. So I'm going to write that down here. Okay, so we have our atomic mass and our atomic number. Okay, so to figure this out, to find the daughter isotope, it is our atomic mass minus 4, so 218 minus 4 is 214. Our new atomic number, which will help us determine what element it's turned into. So Z minus 2. So 84 minus 2, which is going to be 82. So let's figure out what 82 is. So this is polonium. Go back to, we now have lead. Pb is lead. So let's find or finish the equation here. Okay, so we now have polonium 218 decays into lead 214, and cannot forget our alpha particle. And we're done. So that's the first example. So we're doing example 1. Now let's do example 2. Okay, so for example 2, move this camera so we can see it better. Okay, so our next example, we are looking at 226 radium. Okay, so let's find that on the periodic table. So let's see. Okay, so radium is going to be located here. So it's atomic number 88. So we're looking at 226, atomic number 88. Okay. Now we're going to break this down, and again, we're going to do our atomic mass minus 4. So we'll start off with that. So we're looking at 222. So 226 minus 4 is 222. Then we have 88 minus 2 if we follow this equation. So 88 minus 2 is 86. So what is atomic number 86? So this was 88 radium. We go back 2. We go up a row. So we have radon here. So we're up a row. So Rn for radon. We cannot forget our alpha particle here. Okay. So this is going to be alpha decay in a nutshell. So this is just the equation here. Okay, now let's look at beta decay. We're going to look at how to write those equations. Okay, so beta decay is a little bit different, but we do still have some similarities. So we are still going to have our parent isotope, which will decay into our daughter. But we're also going to get an electron and something called an antineutrino. Since this is a beginning level class, and we're not in an advanced chemistry class, we're just in the beginning level class, we are going to focus on just this portion here. We're not going to focus on the antineutrino for this class. This would be more so for an upper level chemistry course, like a nuclear chemistry course. So we won't be focusing on the antineutrino for this class. We're just looking at the parent and daughter isotopes, and then the electron or the beta particle that is being emitted here. Okay, so we have our general equation, A and Z, and again, A represents the atomic mass, Z represents the atomic number or the number of protons. X will represent the element symbol. Okay, we have A again. So the atomic mass will not change. That is different from the alpha decay. And we have Z plus 1. Then Y will represent the daughter isotope symbol. Okay, and then for the beta particle, you can either write that as this, or we can write it as this, as an electron symbol. So either one of those would work. Okay, so let's do a couple of examples. So we are on, should be on example 3 now. So we're looking at iodine 131. Let's find iodine on the periodic table. So we find iodine, and we need to find out the atomic mass, or not the atomic mass, the atomic number, which is the number of protons. So the atomic number is 53. Okay, so now that I have the atomic mass and the atomic number, we're looking at beta decay for iodine 131. Okay, so if we are looking at this, let's go ahead. I'm going to go ahead and write my beta particle first, so I don't forget it. Okay, so I have this. Now for my daughter isotope, I need to have my atomic mass be the same, so that's still going to be 131. Okay, and then I also have my atomic number, which will be different. So instead of subtracting 2 like I did for alpha decay, I'm going to be adding 1 to the atomic number. So 53 plus 1 is 54. So what is 54? Because remember, the atomic number determines what element you have. So if this was iodine at 53, 54 is going to be xenon. Okay, so that is the first example for beta decay. Let's move on to example 4. Example 4, we're looking at thorium-234. Okay, now let's find thorium on the periodic table. So thorium will be right here, down in the actinides. So we have atomic number 90. So I'm going to write 90 right here. That's going to represent Z. Okay, now I'm going to go ahead, once again, I'm just going to write my beta particle. I'll write it like this time around because I'm worried I might forget it later. So I don't want to take any chances. Okay, once again, our atomic mass is going to be the same. So I'm going to keep 234. Now for the atomic number, that will be different. So I will be adding 1 here. So Z plus 1 is going to be my new atomic number. So 90 plus 1 is 91. Let's figure out what element we have. This was thorium. 91 is Pa protactinium. Okay, so now you know how to do nuclear equations for alpha and beta decay, and this concludes this portion of the lesson.